Calculating the hanging mass of a system in equilibrium. This picture shows a hanging mass suspended by two strings. Each string is attached to a spring scale to indicate the force or tension in Newton. We are going to apply concepts that you have learned to calculate this hanging mass. Basic trig functions, vector components, and forces acting on a system in equilibrium. This is your lab report. So we are using the format to show you answers. There are 5 basic steps that you need to follow. The first one, you need to draw a diagram to represent all the materials needed to hang this mass. Then you need to label and measure all variables listed on this table. Then you need to calculate angles theta and alpha using tangent. Please show your work in this box. Then you need to draw a diagram with all forces and components acting on the system. On number 5, you need to calculate the components for each tension. Please show all your work. Finally, you need to find the hanging mass by using all forces. The sum all forces up is equal to the sum all forces down because the system in equilibrium. Then you need to work on your calculated weight, convert to grams, and compare with the real mass that you have in your system. How to complete this lab? First, hold the meter sticks straight as directed. Then identify 2 right triangles and measure the sides A, B, and C, measure in centimeter, and record in your table. Also read the force indicated on each spring scale. Record this force in newtons. That will be your tension 1 and tension 2. Then calculate the value for the angle theta and the angle alpha. So since you have the size of a right triangle, so theta can be calculated by using the tangent, the opposite over adjacent. Likewise, alpha will be the opposite, which is B, over adjacent, which is C. So calculate these angles and record in your table. Now, your diagram, your picture became a vector diagram. So the tension 1 and 2, they are being replaced by those vectors, and the weight force by the vector W. Now you're going to draw all your forces on this grid, indicating all the tensions, the tension, the weight, and the angles. So that's how your grid should look like. So we have here those 3 forces, T1, T2, and the weight. So because these forces, they are not aligned with the grid, so you need to break down into components. So your T1, now we have T1X, and the vertical component is T1Y. The horizontal component for the tension 2 is T2X, and the vertical is T2Y. Now notice that we calculate previously the angles alpha and theta and alpha, but we are using actually this angle X and Y. So to determine this angle X, all that you need to do is subtract 90 from the angle theta. The same thing with y, will be 90 minus the angle alpha. The reason is because we want to use those two right triangles where the hypotenuse are the tensions that we read on the scale. So this is to make an analogy with the previous picture that you have, and now the diagram is converted into all vector system. Now we are going to calculate the components for each tension. So you read on the scale the tension 1 and the tension 2, and you use the sine and cosine to calculate the components. So you need to have handy your diagram. So your tension 1x is adjacent for this angle, so we are using, in this case, cosine. So cosine of this angle is equal to the adjacent, which is T1x, over the hypotenuse, which is T1. So that way you can calculate the T1x. Likewise, you do the same thing for T2x. For T1y, you are using the sine because now is the opposite of x. Likewise, T2y, you are using sine because the opposite of y. Now at this point, you are probably a little bit confused when to use tangent, when to use sine and cosine. So previously, to determine those angles, theta and alpha, you use tangent because you had the opposite, you measure the opposite and you measure the adjacent. So you have those two values, so you can calculate the angle. In this case, you need to find the components of this tension. So this tension needs to be included in your calculation, which is now is your hypotenuse. So for that reason, you are using sine and cosine. So I hope this clear a little bit. And then we are not going to do anything with the horizontal side, because your main goal is to find the weight of this hanging object. So the weight is located on the vertical component. So you are going to, when you break down the vectors into horizontal and vertical components, or X and Y, whatever you want to call, you need to separate both groups. So since you want to know the weight, so you're going to be working only on the vertical direction. So you are not going to do nothing at the horizontal level. But on the vertical level, if you look here, you have those two vectors going up, and you have this vector coming down. So what you are doing is the sum of all vectors going up is equal to the sum of all vectors down. So that is your equation. You know the values T1y and T2y from the previous table. So you add them, and now you have your calculated weight. So now you have your weight in newtons. You want to convert to grams to compare with the engraving mark of that particular weight. So in this case, you are going to use this formula here, mass times 9.8 meters per second square, which is the acceleration of gravity on Earth. And then you calculate the error, the percentage error, how far were you from this real number. So you use this formula, the real weight, which is this, minus the calculated weight, which is this one, divided by the real weight. But actually it's in grams. So, and then you can find your percentage of error. So that's all for this lab. You are using Pythagorean theorem, you are using, not Pythagorean theorem, you are using trig functions, you are using vector components, and you are using system equilibrium to calculate a unknown, in this case we do, but unknown mass.
Alright, so this is a hanging mass suspended by two strings, T1 and T2. The goal of this lab is to find the mass of this hanging weight. Each string is attached to a spring scale to indicate the force in newtons and grams, in mass and grams, produced by tension. A horizontal and vertical imaginary lines are drawn to indicate the lengths A, B, and C. This is A, this is B, and this is C. When measuring a triangle, you're going to measure the inside triangle. So for instance, if I'm measuring this, I would stop at the 8 right here, not up here at the top of the roller. Same goes for over here, stop right here, not over here. Use the lengths provided and apply the Pythagorean theorem and trig functions to calculate the missing angles of theta and A. The system is in equilibrium, which means it's stationary. Use the information provided for each diagram and calculate the hanging mass in grams.